In the natural world, there are many processes happening, all the time. Using the first law of thermodynamics, we can understand how the energy for all of these processes remains conserved. But this doesn't help us understand what processes will happen naturally or spontaneously, and what happens only artificially, that is, with some external help. For example, if we take a glass of hot water and keep it in the open, after a while, it will cool down. From the first law of thermodynamics, we know that the heat lost from the water will have decreased the temperature, or in other words, decrease the internal energy of the system. So these two energies, the heat dissipated and the internal energy decrease, are equal to each other. But the first law does not tell us why this process happens only in one direction. That is, why does the hot water only cool down? Why doesn't the water heat up by absorbing heat from the atmosphere? To explain why processes happen in a particular direction, scientists introduced the second law of thermodynamics and the concept of entropy. Entropy is a measurement of randomness, or chaos. The second law states that processes will happen only if the entropy of the universe either increases or remains constant. To understand what entropy really means, imagine a balloon filled with some gas, which is kept inside an empty closed room. If we open the balloon, the gas will rush outside and will fill the room. But no matter how long we wait, the gas is not going to come back and fill the balloon. It will remain free. If we consider the initial situation, when the gas is inside the balloon, the molecules of gas have very little space to move around. So, the number of positions that each molecule can occupy is limited. In formal definition, we say that the phase space is less. But when we open the balloon, the gas molecules are now free to occupy any part of the room. It has many more options to choose from. So we say that the phase space is more. If we had to guess the position of each molecule of gas at a given time, the chance of us guessing correctly would be much higher when the gas is inside the balloon compared to when it is free in the room. Simply because there are fewer options for the position of gas molecules when it is inside the balloon compared to when it is free in the room. So we can say that, in the second situation when the gas is free, the system is much more random, compared to the first situation, when the gas is inside the balloon. This helps us to understand why the gas will naturally go out of the balloon and fill the room, but it will not naturally re-enter the balloon or fill it. This is what an increase in entropy means. A process will take place only if entropy of the universe either increases or remains constant. But entropy never decreases. In other words, change in entropy of the universe is always greater than or equal to zero. The greater than part is for irreversible processes, and the equal to part is for reversible processes. For irreversible processes, since entropy increases in the forward process, the reverse process is not possible, according to the second law. And this is what makes it an irreversible process. Compared to that, in reversible processes, the entropy does not change, and so the forward and reverse processes are equally possible. The entropy of the universe can be calculated as the sum of the entropy changes of the system, surroundings, and any internal irreversibilities. This refers to any entropy changes that happen at the molecular level that we cannot calculate using macroscopic lab equipment. We can calculate the first two terms from the heat transfer, Q, divided by temperature, D. This is because heat transfer also causes entropy change in the system and surroundings. To understand this, imagine water kept for boiling on the stove. The longer we keep the water boiling, the more it will start to vibrate and even jump out of the vessel. In the same way, providing heat to molecules causes it to vibrate rapidly, that is, increases the kinetic energy of the molecules. When the molecules are moving rapidly, it becomes much more difficult to guess their position at any given time. Or in other words, providing heat increases the randomness, or entropy. So, this is the condition for any thermodynamic process to occur. In the earlier example of gas escaping from the balloon, there is no heat involved. So, the first two terms become zero. But, there is some internal irreversibility at the molecular level. So, entropy change due to internal irreversibility is some positive number. Hence, The entropy of the universe has increased, and the process will occur. But the reverse process will never happen, since the entropy of the system can never decrease. Similarly, if we take the example of a hot glass of water, kept at normal room conditions, the glass will lose heat at a temperature of T glass, and the surrounding air in the room will absorb this heat at a temperature of T room. Since the glass is losing heat, it is written as minus Q. And since the room is gaining heat, it is written as plus Q by sign convention. Consider that there are no other irreversibilities. Then, the entropy change of the universe is minus Q by T glass, plus Q by T room. Since the glass of water has higher temperature than the room, Q by T room will always be greater than Q by T glass. So, minus Q by T glass, plus Q by T room, will always be a positive number. And as a result, entropy change of the universe is greater than zero. Hence, a process will occur only in the forward direction, where entropy increases, and never in the reverse direction, where entropy decreases.